In this lesson, we are going to discuss the basics of assessing a machine learning model. What is meant by training, what is meant by testing and why we do it, what is overfitting, and how you can prevent overfitting in your model. To get some context on the discussion, let's start by discussing the basic workflow for a machine learning project. First step is to gather data. Next step is to convert this data into a form that can be used in your model, i.e. featurizing it. The next step is to train and test your models, and finally to select the best model. These steps are conceptually simple, but to actually master each step requires great expertise. We'll be covering steps 1, 2, and 4 in much more detail later on in the course. But to get started as soon as possible, it is essential to understand step 3, which is what we'll discuss now. A machine learning model is just a mathematical function. It takes an input, a vector, it performs some computation with that vector, and then it yields some output, which we call a prediction. Such functions have a good number of free parameters, and depending on the values of these parameters, you will obtain different predictions given the same input. To train a model is to assign these parameters such values so that the predictions are what we desire. And what we desire is for the predictions to always be the same as the actual labels. Unfortunately, we do not have this information. Otherwise, we wouldn't need a machine learning model. We could simply use a dictionary that tells us the answers. So what we do instead is pick our parameters so that they have some desirable properties. For instance, perhaps they have the highest accuracy or highest F1 score on our data, and we assume that the model will perform well on data we have not seen before, i.e. generalize. However, if this is done incorrectly, what will happen is that your model will perform well on the data you gave it, but then when you put it out in production, it will fail you. And this is what is known as overfitting. In order to prevent overfitting, what we do is split our data into a training set and a testing set. We train our model on the training set, but the testing set we only use to measure the performance of our model. We don't train on the testing set, and we try to touch it the least possible, because every time you use the testing set, you are leaking a little bit of information and you are increasing your odds of overfitting. Assuming that your data is not biased in some way, the performance that you have on the testing set is an accurate measure of how your model will perform in actual production. Let's load the iris dataset, which is a standard dataset in machine learning consisting of the measurements of petals of different iris flowers. As far as datasets go, this is a nice one. It is balanced, it doesn't have any missing values. It's pretty small. As you can see, each vector is 4-dimensional, so just 4 measurements. There are 3 different targets with 3 different possible flowers that a measurement can correspond to. I'm going to declare a simple yet effective classifier, a decision tree, which basically consists of a series of decisions. For instance, is flower petal width bigger than 3 or less than 3? And depending on that, it will continue making decisions until it reaches a conclusion that it is iris of type A or B or C. I'm going to fit this classifier to the data, and then I'm going to score it simply getting the accuracy. And the accuracy is 100%. Holy cow. Unfortunately, if you took this model and then used it to predict new samples, you discover that it doesn't do too well. The problem is that we overfit. Essentially, the way we approach the problem, the classifier simply memorized all of the data and performed perfectly because it has all the answers memorized. But when you show it something new, it will not perform as well. To address this problem, what we do is something called a train test split. Basically, we subdivide our data set into a training set, the data set that we'll be using to create and fit the model, and then a testing set that we'll be using simply to evaluate it and make sure that it didn't memorize it or not capture any information. So we're going to go ahead and fit the classifier to the training data and then score it on the testing data. And as you can see, the performance has dropped. Not too much, meaning that the classifier seems to be performing quite well, but certainly not 100%. And in practice, you'll find out that this too is probably an overestimate, because in real life, there will be some unforeseen new data. Next up, structured learning with XGBoost. See you there.